Big Bang is in a certain sense not singular at all. Well, it's not singular if you use a kind of geometry which is called conformal geometry. Now, conformal geometry is the geometry of angles.
The cosmos's mysteries have captivated humanity for centuries, from space to subatomic realms. Unveiling secrets challenges our understanding of reality. The origin of the universe is a long-standing question, with the Big Bang theory supported by evidence. Yet, what caused the Big Bang remains intriguing. Some propose our universe emerged from a prior one, challenging a definitive beginning. Conformal cyclic cosmology, introduced by Sir Roger Penrose in 2020, explores this concept. In this episode, we'll delve into Penrose's groundbreaking theory, challenging conventional beliefs and offering innovative pathways for cosmological exploration. This is Reveal the Mystery. If you're curious to learn mysteries of the world, space and beyond, consider subscribing. In the early 1900s, most scientists believed that the universe was unchanging and didn't expand or contract. However, about 100 years ago, astronomer Vesto Slipher noticed some nebulae moving away quickly. At first, people thought it was because of our Milky Way's motion, but observations from the Lowell Observatory in Arizona didn't support this idea. Then, Edwin Hubble came in and discovered a pattern. The farther a nebula was, the faster it moved away. This matched what general relativity predicted, showing that space-time could stretch or shrink. Following Einstein's equations, we trace back the universe's expansion to a tiny point called a singularity. This idea led to the concept of the Big Bang, suggesting that the universe started explosively from this point. However, what happened right before the Big Bang remains a mystery. If everything began from this singular point, we wonder if there was truly nothing before it, no space or time. To comprehend the temporal rewinding billions of years ago, envision the universe as the surface of a balloon. Introducing the scale factor, akin to a ruler measuring the balloon's size, the universe is currently at a certain size, designated as one scale factor. However, in the past, this balloon was smaller. Analogously, two dots drawn on the balloon move farther apart as it inflates, illustrating the expansion. Conversely, deflating the balloon brings everything on its surface closer together, resembling the singularity, a time when the universe was exceedingly hot, dense, and closely compacted. Yet, delving into this notion reveals complexity. While Einstein's equations point towards a singularity, compelling evidence suggests caution. Observations hint at a moment just before 10 to the minus 32 seconds, indicating a rapid expansion known as cosmic inflation. This inflationary phase offers insights into the universe's large-scale expansion, explaining its uniformity and the formation of galaxies. While resolving certain puzzles in the Big Bang theory, the singularity, marked by intense density on a minute scale influenced by quantum forces, remains elusive through general relativity alone. Acknowledging this early rapid expansion might prompt a re-evaluation of the traditional Big Bang Singularity concept, potentially reshaping our understanding of cosmic inflation and the universe's inception. So, delving into the origin, the Big Bang Singularity might not offer the complete narrative. The use of complex mathematical concepts like singularities often indicates gaps or stretching in the theory. Currently, we rely on general relativity to rewind the universe, but it falls short, especially under the extreme conditions of the Big Bang. General relativity and quantum mechanics don't perfectly align in the super-dense and hot conditions of the Big Bang Singularity. The true commencement of space and time remains uncertain. Some scientists contemplate that replacing Einstein's theory could alter the narrative, suggesting the Big Bang might not mark the beginning. There could have been preceding events leading to the formation of the universe, galaxies, and stars. Sir Roger Penrose introduces a new perspective, prompting us to envision the universe at infinite time. In this scenario, as time progresses, entities like black holes vanish, leaving behind photons, particles of light. Photons exhibit a unique behavior in space-time. If we imagine space-time as a grid where separation is measured using an equation involving time and space, photons move uniquely. They traverse this cosmic grid without experiencing time or space, like instantaneous travelers. Consequently, the space-time interval for photons approaches zero. In a simple example, when you turn on a flashlight, event A, and the light reaches a certain point, event B, the space-time separation is nearly zero, as light covers both time and space simultaneously. Photons lack a rest frame or a personal clock, defying our common experience of time. This aligns with the fundamental physics idea that light consistently moves at the same speed, regardless of one's location or motion. The Maxwell equations governing light exhibit conformal invariance, meaning they don't distinguish between scale changes. Whether a system is stretched or squashed, it remains unaffected. Picture the Big Bang like a one-time surface, but imagine going back before it. It's like a math trick to describe how the universe initially looked. In this way of looking at things, every space is the same for things without mass. These things, like light, see all spaces similarly but don't experience time passing. Einstein's theory helps us understand when the universe began by connecting energy and mass. Another equation by Max Planck links energy and frequency. So anything with mass, like a rock or an apple, has its own rhythm. Without mass, there wouldn't be a clock or time. Sir Roger Penrose's idea suggests that the far-off future is like a new Big Bang. The universe would become mostly empty except for photons. This challenges our usual ideas about the start and end of the universe, known as conformal cyclic cosmology. If we think about a cyclic model, it was initially wrong. The focus was on the scale factor, but we should look at the Hubble radius. When we talk about a cyclic universe, it means it should look the same from one cycle to another. The Hubble parameter shows how fast the universe expands initially. The universe began as a tiny ball, about 10 to the power of minus 25 centimeters, bouncing up with a lot of energy. As it rises, the speed slows down, and so does the universe's expansion. When it descends, the Hubble parameter drops, and the universe shrinks back to 10 to the power of minus 25 centimeters. Just before landing, there's a push, our universe's dark energy, causing a contraction. The nudge from dark energy makes the universe expand again in a continuous cycle, similar to the conformal cyclic cosmology model. We aim to develop a comprehensive theory intertwining the past, present, and future seamlessly. Consider the concept of now. In daily life, time feels like a continuous stream, yet it can be viewed as a series of snapshots. Envision all events occurring simultaneously, from the Big Bang to current happenings, captured in a single now slice of space-time. Einstein's relativity alters this common-sense view with motion. In cyclic cosmology, different ways of slicing this region represent individual now slices, and someone in motion perceives a distinct present. Imagine an entity in a distant galaxy. As it moves, its now slice cuts through the region differently, retracing the past or glimpsing into Earth's future when moving toward it. Understanding time slicing resembles seeing a series of snapshots encompassing past, present, and future, especially when considering photons. It's akin to fitting moments into a space-time tapestry, challenging the notion of a continuous separation between past, present, and future as an illusion, as Einstein proposed. Sir Roger Penrose proposes an intriguing perspective on the universe, suggesting it perpetually restarts, transitioning from one significant explosion to the next in an infinite cycle. However, pinpointing the precise origin or conclusion of the Big Bang within this cyclical framework poses challenges. Amid this intricate portrayal, a captivating notion emerges. Our universe is in a constant state of growth, generating new universes within itself. The majority of space undergoes perpetual expansion, leading to a concept known as eternal inflation, sustained by quantum fluctuations. This notion extends to the idea of a multiverse, where every conceivable event repeats endlessly. Recent events, such as the 2014 claim of detecting cosmic gravitational waves as proof of inflation, have instigated skepticism. Discovering these were patterns caused by light passing through our galaxy's dust raised doubts, prompting a re-evaluation. Some scientists are revisiting the Big Bounce theory, an alternative to the Big Bang, suggesting the universe's smoothing results from gradual contractions rather than rapid expansion's random quantum effects. Ongoing experiments are scrutinizing this theory, exploring the potential absence of cosmic gravitational waves. The Big Bounce proposes a cyclical universe, and the outcomes of these experiments will significantly contribute to understanding the universe's origin and future, whether it's a chance occurrence in an expansive multiverse or a well-structured representation of everything.